Hey everyone, welcome to our YouTube channel. In this video, we'll be learning about bias variance trade-off. So in order to understand about bias variance trade-off, we need to be acquainted with certain terms and terminologies. Let's understand what are they. So first thing is overfitting. Overfitting means when the model gets excessively well trained in the training data, but cannot really reproduce the same results in the testing data set. Then we have something called as underfitting. That is exactly the opposite of overfitting. It cannot really It does not get trained properly in the training data, and again, as a result, it does not perform well in the testing data as well. Then we have something called as bias and variance. All right. Let me just reformat the same. Okay. So this should be the agenda of our session today. And if the context is clear, let's learn all these terms and terminologies so that we get an understanding about what bias and variance actually is and why there needs to be a trade-off between the two. All right. Great. So let's start with overfitting. Now, overfitting is it occurs when the model learns not only from the necessary patterns, but also from the noise attached with it. So what do I mean by that? Let's do a simple, let's take a simple example. Okay. So let's say we have a scatter plot, something like this. Okay. And we have our points. Okay. Make it a bit more complex. Yeah. Now we have already learned about linear regression, right? What would be the best fit line? Something like this, maybe, right? Let me just make it a bit thicker. Something like this might be a linear regression line, right? Or the best fit line. But when we talk about overfitted model, the line would change something like this. Let me take a different ink. So it will try to fit all the given points. Okay, something like this. And you understand how complicated the model became, right? Initially, this was a very simple model, simple linear regression model. But now it has become a very complicated model. Overfitted model. Okay. Now the point is, so can we say that overfitted model is better? The answer is absolutely not. Why not? So let's understand this with an example. Let's say you have your exams sometime, let's say tomorrow, and as a result of which you get some practice papers, mock papers, right? So this is you. Please pardon my drawing. And let's say you get some practice papers or mock papers. Now, since you have your exams tomorrow, you practice all the questions from this practice paper and you give mock test based on this practice papers. One of this practice papers, let's say you got something around 10 papers. You practice the questions present in this 10 papers and you give your test. So mock test. Mock test is from any of this 10 papers. And since you had practiced thoroughly, really hard, you got a full 100 out of 100 in your practice test. So tomorrow you went to the exam hall pretty happy that you will be, killing the exam. So in real exam, you got something around 20 out of 100. Now, why is this the case? You did study hard, right? You practiced all the questions present in these 10 papers, but you still got, you got 100 out of 100 in your mock test. But in real exam, you got a 20 out of 100. What went wrong? The thing is, let's say in these 10 papers, you got around, let's say, 250 odd questions. So you practiced all these 250 questions, but you never understood the concept. So you understood the 250 questions, but concept was not clear to you. And in real exams, 20 questions out of the 100 questions came from this 250 question paper, the question bank that you have studied. The rest 80 were unknown to you. Now you did not understood the concept, right? You did not understand the concept. So the alien questions, the unseen questions could not be answered by you. You could only answer the 20 questions that were common from the question bank. That's why, although you prepared really well, you got only a 20 out of 100. And this is a classic case of overfitting. So what happens over here is, this is the training data set. In the training data set, the model gets really overfitted. It learns or memorizes all the issues, all the noises, and everything in the training data set. Therefore, it performs really, really well when the training data set is given. But once it is exposed to the unseen data, the alien data, it starts behaving weird. It cannot really perform well. It performs very poorly on the testing data set. So our goal is to reduce, whenever we see an overfitted model, our goal is always to reduce the overfittedness, all right, to make it more generalized. So the model performs well on the training data set, but it performs poorly on the testing data set, right? This is the example of a overfitted model. Now, what is underfitted model? So an underfitted model is unable to learn the underlying patterns, probably due to missing complexity in the model or less features in the model. Now, what do I mean by that? Again, think of it like a situation. So imagine the same situation, right? Uh, you have your exams tomorrow, but this time you study only 10% of the practice papers. So what happens is, this is again you, right? And you have your exams tomorrow. You have around 10 practice papers, out of which you had around 250 question, right? And you practiced only, let's say, 25 questions, 10% of the questions. So you practiced only 25 questions. Now, what would happen is, you will still score poorly in the real exam. But in addition to it, you will also score poorly in the practice paper. So mock test, here also you score poorly. Let's say you score around 12 out of 100. Why? Because out of the 25 questions, sorry, out of the 250 questions present, you practice only 25 questions, and probably the 100 questions that you attempted, out of which only 12 came common. So you got 12 out of 100. And in real exam, you might get anywhere between 0 to 25 out of 100 because you practiced only this 25 questions. So this is what underfitting means. In overfitting, you at least practice the entire mock tests. So there is a possibility that you can still perform well in the real exam. But in underfitted model, there is absolutely no chance because you did not practice well. So think of it as a lazy student who does not study, right? And gets poor marks both in mock tests and in real exams, right? Now, what should the ideal student do? these are two cases of students, right? One is a student who is slightly, I would say, for lack of better words, maybe dumb or stupid in nature, who memorizes the questions and the answers, not the concepts. As a result of which, even after working really, really hard, he gets poor marks in the real exam. Another student is a lazy student. He doesn't really work hard, therefore, he gets poor marks both in mock test and the real exam. Now, if the student was an ideal student, what would he do? He or she do? So, an ideal student understand the concepts, right? Not memorize, but understand the concept and practice enough so that he can solve new questions that might be encountered in the real exam, right? And this is exactly what we want in an ML model. Okay, so this is exactly what we want in an ML model. The first thing is that the model should learn patterns and not memorize. So, model should learn patterns and not memorize them. Okay. The second thing is the model should not be too simple. The model should not be too simple. So I hope these 2 points is very, very clear. The first point, model should learn patterns and not memorize them. That is, it should not be the dumb student. And the model should not be too simple. That is, it should not be too lazy. It should also work hard, practice enough, right? So this was the concept that you should know about overfitting and underfitting. Now let's move to the next part, which is bias. Now, what is bias? Model makes strong, oversimplified assumptions and never really learns properly, right? Think of it like the model has wrong understanding of the problem from the very start. So let me also, or I hope you understand, right? The model from the very start started understanding the problem very differently. A classic example of an underfitted model. It did not study enough, so it has a very wrong assumption of what the problem is. So imagine that again, you're a student and you think that math means or all math problems can be solved by simple addition. All right. So even if the problem needs a multiplication or division or any other operation, right? You as a student keep on adding it. So what happens? So let me again take the ink. So you're a student, right? And you think every math problem means addition. That's all. Now, when other operations come into picture, let's say subtraction, multiplication, or division, you simply add. All right. As a result of which, what happens? In mock test, you still get poor marks. And in real exam, you still get poor marks, right? Why this happened? Because you thought, I mean, your thought was too simple, right? Because your thought was very simple. You only thought math means addition, while it could be other things like subtraction, multiplication, division. You did not study your context well. You did not study your resources well. You did not study your textbooks properly. That's why you thought math means only addition. So whatever problem comes, I'll only add. And as a result of which, you got a very undefeated model, right? So this is bias. The model makes strong, oversimplified assumptions and never really understands the context properly, right? So high bias leads to underfitting. Whenever you are highly biased, that is, you are too simple, you are not studying the entire context properly, it leads to an underfitted model. So you can see the data is something like this, but your answer is always a linear straight line, which does not capture enough number of points. So getting a very poor performance, right? So high bias leads to underfitting. Next, let's come to variance. So what is variance? It's basically a measure of how much a model's prediction can change when trained on different data sets. Now, what do I mean by that? Again, let's take the example of the student. So let's say here the student memorizes, let's say as a teacher, you have given uh, certain homeworks and you have asked the students to come prepared with the homework so that they can also perform well in next day in the classwork, right? Now, what does the student do? Student memorizes today's homework perfectly, right? He works hard for the homework, right? And tomorrow comes prepared with the homework. Now, tomorrow in the classwork, the teacher changes the question slightly. Now, what happens? The student gets confused. So he got full marks in the homework because he really worked hard with the homework, but he memorized those questions. But in the next day, in the classwork, he got very poor marks. Questions were of the same concept, but the questions were designed differently. Since the student worked really hard with the homework, not understanding the concept, but just to answer those homework questions, he performed well in the homework. But in the classwork, he got very poor marks. This happened because the student learned all the details and not the main idea. And this is what we call as variance. What happens? The model fits the training data too well and fails on the new data set. So this is the training data set, and this is how the points are. The model overfits. The model fits all the points in the training data set. But when it encounters unseen data, it fails. It performs poorly. And this is exactly what happens when we have high variance. So high variance leads to overfitting, right? Now, what should be an ideal scenario? What do you think? What should be an ideal scenario? Ideally, The student should understand the concept, right? And not the wrong ideas. So understand concepts and not memorize, right? That is low bias. Or understand concepts and not wrong ideas. That is low bias. Second, it should not memorize blindly. So not memorize blindly. Okay. That is, it should have low variance. When it understands the concept, it is not biased, therefore low biased. And when it does not memorize blindly, it doesn't get overfitted to a particular training data set. So low variance, right? Now, again, this is an ideal ML model. The ideal ML model, so the ideal, just give me a moment. Yeah. So the ideal ML model is one that has low bias and low variance. Okay. So an ideal ML model is one which has low bias and low variance. However, in practical world, this is impossible to achieve. We cannot achieve both together, right? So here is where the trade-off between bias and variance comes into the picture. Okay. So let's come over here. But before coming to bias variance trade-off, let's quickly have a revision of what we understood. The first thing, overfitting, it occurs when the model learns not only from the, not only the necessary patterns, but also the noises attached with it. Therefore, the model performs well on the training data set and poorly on the training data set. What is underfitting? In underfitting, the model is unable to learn the underlying patterns at all. And as a result of which, it performs poorly on the training data set and also poorly on the testing data set. Bias is what leads to underfitting. Okay. Because the model is too simple. It doesn't learn all the patterns. It is biased enough to learn the patterns, underlying patterns in the data. So it leads to underfitting. Variance is when the model uh, changes its prediction too often with changes in data sets. That is, it overfits the data that is given to it highly without understanding the underlying concepts. It tries to memorize the data points. So high variance leads to overfitting. And in our ideal situation, the model should have low bias and low variance. But as I mentioned, this is hard to achieve in practical world. Why is that? So this is what we would be getting an answer to in bias variance trade-off. So ideally, a model should have low bias and low variance. However, as I mentioned, it is impossible to achieve both simultaneously. So a model with high bias and low variance is too simple and may not capture the underlying patterns in the data, leading to underfitting. Conversely, a model with low bias and high variance is too complex and may fit noise in the training data, leading to overfitting. Now, why do I say low bias and sorry, high bias and low variance or low bias and high variance? Can I not say low bias and low variance? The answer is no. If you look at the bias variance trade-off curve, this is how it looks like. When it has high bias, it would automatically have low variance. This is the curve for variance, right? So when it has high bias, right, this point over here, right, this point over here. So when it has high bias, it would automatically have low variance. And when it has high variance, it would automatically have low bias. Both bias and variance cannot be high or low simultaneously, right? Think of it like, um, let's say, if you, let me think of an example. Let's say if you make the student too simple, if you instruct the student to be too simple, right? It would have high bias because it is very simple. It doesn't understand the complexity of the real world. So it would become automatically high bias model. But if you want the student to be too detailed, it would become high variance model, right? So in simple words, high bias or low bias and low variance together cannot really coexist. And therefore, we have to settle down somewhere in the middle to find a sweet spot somewhere in the middle. So this is our sweet spot. Okay. Now, how to really fix this? To reduce bias, right? To reduce bias, let me just come over here. Or let me just use an ink instead. Okay. So let me see. Same thing. How to fix. To reduce bias, we can teach more to the student, right? So teach more or add complexity, let's say, which invariably means adding complexities. What do I mean by adding complexity? That is, encounter the student with more complex data points or more features, right? So invariably add more features or go for better models. Okay. And how to reduce variance? Control and generalize. So bias is a student who is too dumb, right? So here it's an example of dumb student. While variance is an example of student who memorizes too much. Let's say student memorizing. Okay. So what we can do, we can control the student, control and make him generalize. That is, understand the concepts. Understand concepts and not memorize. Okay. What else? There's something called as regularization. And this is exactly what we do in ML. It penalizes the model for memorizing the data points. So penalty given for memorizing. Now, if you start memorizing, I'll give you penalties. You have to, adhere to some penalties. So you need to understand the concept and not memorize things. There's another method called as bagging, which are bagging and boosting is a part of our ensemble techniques, which we'll again learn in later lectures. So what bagging does is it helps the student learn from different resources. So learn from different resources. That is, do not be, contented with only one textbook. Learn the concept from different textbooks so that you are not memorizing what is written in one particular textbook, but you are understanding the concept. Because if you read different textbooks, if you read different questions, you will have an overall idea. Probably you can memorize 200 questions, 1,000 questions. But what if there are a billion number of questions? You cannot memorize all billion questions, right? And for how long? So if you understand the concept, the underlying concept, then you will be able to reproduce any other questions given. So this is what bagging helps us do. It helps the machine learning to learn from different resources so that the machine does not memorize the concepts but understand in a generalized manner. Then we have something called as boosting. What is boosting? Learn from your past mistakes. So learn from past mistakes. So what happens is the model keeps on making small errors. And what boosting helps it to do is understand from its past mistakes to keep on, improving the model sequentially one after the other just by learning from its past errors. So this is how we actually go ahead and fix our ML model, right? In the next lecture, we'll be learning about regularization. And we'll do a code follow up, a practical implementation of regularization as well to understand how we fix our variance. All right. So see you in the next lecture. Thank you.